Okay, so then in 5b, we're using the same skills, but we're introducing you to a new idea where we're not just finding the area under the curve, under the function, but we're finding the area between two functions. All right, so if we have one function f of x and another function g of x, and let's say they intersect at a and b, then the area is going to be the integral of the top function, take away the bottom function over that respective interval. All right, so we'll get straight into the examples. Find the area enclosed by the function f of x equals 4 and g of x equals x squared. So it can help to sketch this, right? And if you sketch the function x squared, we're pretty familiar with parabolas. They look like this, right? That's y equals x squared. Okay, here's x, here's y. And then we've got the function y equals 4, which is just a horizontal line, isn't it? It's a horizontal line at 4, and it's going to be this one here, y equals 4. And so we're asked to find this area, the area enclosed by the function y equals 4 and y equals x squared. So it's going to be the area of the integral of the top one, take the bottom one. But first we need to determine what are these points of intersection? When do they meet? And they're going to meet when the functions equal one another, right? Functions intersect when they are equal. Okay, so here's the first function, here's the second function, we make them equal, and then we just solve through. What are the x values that make them meet? Perform the square root of both sides, we'll have plus or minus 2. So here we've got x is minus 2, here we've got x is positive 2. So that means for this first question, we're doing the integral from minus 2 to positive 2. I'm going to do it up here and then I might run it, just run it out of space, I think. Integral from minus 2, positive 2 of the top function. Okay, so the top function is 4. Take away the bottom function is, all right, the function underneath is this one, x squared. All right, now you absolutely must put brackets around the second function, because if there's multiple terms, the negative needs to distribute, right? So we're not going to get caught out here, but in the future, always put brackets around it so that when the negative will distribute in there accordingly. All right, and then you just integrate it as you normally would. Distribute the negative, integrate as you normally would. So this goes to 4x, all right, and this goes to x to the power of 3 on 3. Now I'm going to make this a little bit easier for myself, okay? Because notice how this area, it's symmetrical about the y-axis, all right? This area here is the same as this area here. So another way I can say that it would be true is that the whole area is equal to 2 times this area. All right, and what that's going to allow me to do is substitute 0. 0 is heaps easier to deal with than putting in minus 2, right? There's less calculations for us to do. So I just want to show you that's something you can do if it is symmetrical. So let's even make the statement first before I perform the integral. This is also equal to the 2 times the integral from 0 to 2. All right, so the integral from minus 2 to 2 would also be equal to 2 of these ones, because it's symmetrical, right? And so that's what I'm saying there. Okay, so I'll just make the statement first and then we'll perform the integration. It's going to make it a fair bit easier for us. 4x, take x to the 3 on 3, from 0 to 2, sub in the 2, sub in the 0. Alright, so that's when we put in the 2, take away when you put in 0, it's just 0. And so we'll evaluate this. We've got 16, take away 8 on 3. So we've got 2 lots of 16, take 8 on 3. And remember I've said as well, like, what are you required to show? So you're required to write the statement, show the integration, sub in the numbers, and then really we're just required an answer. So you can put that in. There's a fair bit of syntax. Putting this in is going to be a fair bit easier. It's going to get you the right answer straight away. But if you want to go follow this through, if we have 16 take 8 on 3, before we can perform that, they need to have the same denominator. So 16 is 48 on 3. So it becomes 40 on 3. And we have 2 lots of it, it becomes 80 on 3. Okay, that's what it's going to evaluate to. You can use your calculator to help you out. Area, so units squared. the area between these 2 points, 80 on 3 units squared. Alright, very good. Any issues? Cool. So let's move on to the next one then. You can use your calculator. And so like let's talk about here with this one, we have the function e to the x take 5. Alright, and so if we sketch that, this is what it's going to look like. It's going to look like, here's the y-intercept of minus 4 is the y-intercept. So it's going to look like this, and then it's going to touch here somewhere. Okay, you can sketch it on your graph. That's a y-intercept of minus 4. Now we are asked, let's read the question carefully, find the area enclosed by. Another word you'll read is bounded by, like this area is constrained by the y-axis, the x-axis, and the function. So it wants this area, right? That's what it wants, this area here. And so the area is going to be the top function, take the bottom function. What's the top function? What's the top function? What's the equation of this line? Very good, it's the x-axis. The equation of this line is y equals 0. So we have our top function, y equals 0, and we have our bottom function, e to the x take 5. We're integrating from x is 0 to this point here. We don't know this point here. We could g-solve it, all right, and round it, but let's get it exactly. This is the x-intercept. X-intercepts occur when y is 0, right? That's when e to the x take 5 equals 0. All right, so we'll add 5 to both sides. E to the x is 5, and then ln both sides. We've got x is ln of 5. All right, so this x-intercept here is ln 5. Okay, we've got all the goods. Let's evaluate it. So, we have the area of 0 to ln 5 of the top function, take away the bottom function with regards to x. Now, integral of 0 would be 0x, all right? So the only reason I'm writing this out is to point out whenever you're finding area under the x-axis, it's always the negative of the function. So this is just going to simplify to this, right? From 0 to ln 5. So whenever you're finding area under the x-axis, it's just the negative of the function. Okay, we've distributed the negative the whole way along. I should put that down here to demonstrate it's not power. Okay, so that's what we're evaluating. Let's go through and do that. Now, the integral of e to the x is just e to the x. The negative just hangs out the front. Integral of 5 is 5x from 0 to ln 5. We'll plug that in. Now, remember I've said, like, you know, when you're putting 0 in, it can tend to 0. That's if everything's x to the power of n. But here when we have e to the 0, that goes to 1. So you can't just completely disregard that side of it, as we've done in some instances. You have to be careful. You have to have that sort of intuition. Is it going to 0 or is it going to be something else? All right, let's process here. That's minus 5. We've got plus 5 ln 5, and then we're taking away, this is minus 1. That's 0. All right, so if we have, these are like terms, minus 5 take away minus 1, that's going to be minus 5 plus 1. So we have 5 ln 5, take away 4. All right, that's going to be our area exactly. Now, you can get these on your calculator, all right? You can check on your calculator. We can graph this function, e to the x take 5, and g-solve the integral, all right? And there's a number of options. I'm going to travel around and probably show you guys individually and get you to practice using it because it's a tool that can really support us. Okay, last one. Find the area enclosed by the x-axis and sine x over the interval 0 to 2 pi. Alright, so I'll clear this again. We're going to sketch it. F of x is sine x from 0 to 2 pi. So if you graph the function sine x, right, amplitude of 1, it starts here, has a wavelength of 2 pi. Sketch it properly, up, down. Alright, it says find the area enclosed by the x-axis and the function. And so what that means is it wants us to find this area and this area. Okay, it wants us to find both and add them together. So we can do exactly what we did before. Because it's a periodic function, it's a trig function, it's symmetric about the x-axis, right? So the area of this region is equal to the area of this region. And so the initial statement, like we can treat it two ways, all right? If we wanted to be very precise, knowing what we understand, now this point here, halfway, that's pi, we would have the integral from 0 to pi of sine of x, okay? That's going to give us the top area. If we want the bottom area, we're going to have plus the integral of the negative of sine x. All right, the negative of sine x because it's below the x-axis. Remember, when area is below the x-axis, we have to make it the negative of the function because it's the line y equals 0, take away the function, plus negative sine x from pi to 2 pi with regards to x. So that's one way that we can find this area. It's not the easiest because it involves a number of integral operations and substitutions and so forth. Definitely the easiest is if we recognise that they're symmetrical, it's equal to 2 times the integral from 0 to pi. Okay, we're saying these areas are the same, so we can just find one of them and double it. All right. Okay, let's come up here and perform it. So we've got integral from 0 to pi, we've got 2 lots of it, sine x, that's what I'm performing. Integral of sine x is negative cos x. Alright, 2 is hanging out, sub in the pi, minus cos of pi, take away minus cos of 0. Alright, so I'm using brackets heavily here. So that's when we sub it into the first one. That's when we sub it into the second one, keeping in mind the negative there. Now, we'll evaluate it. Cos of pi is minus 1, so we have minus 1, it becomes positive 1. Take away. Cos of 0 is 1, so we have minus 1, but then there's negative here, makes it positive 1. That's 2, 2 times 2, 4 units squared. Alright. So, yeah, requires a bit of thinking about often finding points of intersection and so forth. It'll start pretty easy and it'll get progressively more complex. It's a beautiful exercise. I hope you enjoy it. Let's get into it.